Yeah.
Share screen actually disabled for me.
Yeah.
Good afternoon, everyone. My pleasure to introduce you today's this afternoon's speaker, Dr. Bablu Mukherjee. So, Bablu Mukherjee is currently working as a research fellow at the Center for. A lot of noise is coming. Dr. Bablu Mukherjee, can you hear? Dr. Bablu Mukherjee is currently working as a research fellow at International Center for Materials Nanoelectronics at NIMS, Tsukuba, Japan. He graduated with his master's degree in physics from Indian Institute of Technology, Madras in 2009. And he received his PhD degree from NUS Singapore in 2013. He was a GSVS fellow at NIMS and DA fellow at Gottfried Wilhelm Leibniz University of Hanover, and then postdoctoral scientist at George Washington University, and Institute postdoctoral fellow at IIT Bombay. His research interests are in the areas of nanofabrication, photodetectors, non-volatile memory, nanosensors, and optoelectronic devices based on 2D materials. Now I request Dr. Bablu Mukherjee to start his presentation on 2D materials and van der Waals heterostructure-based optoelectronic devices. Dr. Bablu Mukherjee.
So thank you, Professor Asutosh, for your kind introduction. And thank you for inviting me. So good afternoon, viewers. Now I am going to talk about 2D material and van der Waals heterostructure-based optoelectronic device. So basically, I will give a very brief overview of various projects which we are working in quantum device engineer group and NIMS. So here is the outline of my today presentation. So I'll start with introduction of 2D layer crystals, and then I will cover many applications towards photodiode, phototransistor, light assist memory operation, logic gate operation, and also finally light emission. So there is a story, 4-minute mile, and that story is quite connected with 2D materials. So until 1954, it was thought that human cannot complete a race of a mile under 4 minutes. But however, later we see Roger and later on John, they made it success. So basically now it is a commonplace and human is capable of doing this. So similarly, until 2004, based on thermodynamics, it was thought that 2D layer material of one atomically thick, cannot exist. However, Professor Game and Novoselov, they invent a one atomically thin layer of carbon material. And later on, we see various 2D materials come, starting from graphene, hexagonal boron nitride, and huge member in transitional metal dichalcogenides and black phosphorus. And we see variety of various exciting properties is band gap variation starting from 0 to until even 7.2 eV as we've seen for HVN, and various electronic properties. and it is quite easy to fabricate. And so we just need to have a scotch tape, and we take crystal and do manifold, and we can just deposit in any substrate we want. And that's a simple process. And we have variety of crystals starting from conductor, insulator, and semiconductor, and that all needs for for device application. Of course, there is a for large scale growth, there is a many various techniques available, starting from chemical vapor deposition technique, and you can see here is like a PCBD, MB, and an LP. So some of them are is settled in industry. So basically, we can have now big range of this 2D material, even centimeter by centimeter scale, and we have the Wells technique process to deposit in various substrate. So now I will show you why this 2D material is really promising and interesting for electronic device application. So this schematic diagram, so one-dimensional cross-sectional image of a field effect transistor, and what we apply a drain bias at the at this transistor, so that drain and potential distribution across the x is depend on this Poisson equation. So this and the solution is depend on this exponential form, where this function decay along x direction by this characteristic length of lambda, which depend again on this bulk thickness and oxide thickness of this transistor. So if we want to scale down the transistor, and if we want to further reduce and go towards nano region, then basically this there is a limitation. So the channel length cannot be below 5 times of this characteristic lambda. And if it does so, then there will be a high leakage, and basically the transistor operation get collapsed. So there we need to think of alternative materials, and there 2D materials, it has a great potential because it do not have any dangling bonds, also surface roughness, and that give advantage. So here we can see if the thickness of this 2D material go even below 1 nanometer, the mobility don't decrease. Whereas for 3D semiconductor like silicon or indium gallium arsenide, it depend on T to the power 6. So now you are convinced that okay, this 2D material is a really eligible candidate and interesting for electronic material in the nano range and in nano world. So here I will show the various applications. So here what we see in this optical image, we start with a graphene, and then we deposit hexagonal boron nitride on top, and then RES2 on top. So we have now heterojunction of heterostructure of various 2D material, starting with conductor, insulator, and semiconductor. And we can have different combination on a single chip. So it can have photodiode, phototransistor, and memory device. So some of them I will discuss in next few slides. So I'll start with this photodiodes. It is a very interesting what we observe that the thickness of RES2, if it combine of thin and thick, then that actually can show high responsivity for sensing application, and also it shows a fast response in the device. So of course, there are various issues in an industry in terms of doping control, and also area selectivity, stability, and also getting atomically flat surface. But there are also some, some negative points from monolayer TMDs, because the thickness of this material is very is like atomically thin. So the light absorption is not so strong for applicable in this optoelectronic device. So that is the also one drawback. So we need to at least need some thickness so that the light interaction can occur strongly, so that optical absorption can be higher to have a real device application. So in that prospect, we can use a two-dimensional radium disulfide, because it has thickness independent band gap. So even though we take few layer of thickness of this material, it shows like a direct band gap, and that will have high absorption. So it is so strong optoelectronic response. So this way, and so that's why we select rhenium disulfide as a active material for optoelectronics. So here, how we do fabricate this PN diode. So we basically take this type of N-type semiconductor and we deposit on highly doped silicon substrate, and that give a interface which looks like type 2 band alignments and PN diode. And the basic characteristics for a PN diode is shown here. It's typical schematic of this behavior. And we are interested in this reverse bias region where it has a sensing property. And of course, it is a vertical integration. So we have small interlayer spacing where we can apply high electric field to dissociate the excitons. And also it has large exposure area in 2D surface. So it will have high sensing. So to start with this fabrication process, we need to have some initial template. So we use 4-inch wafer and we go various methods to fabricate initial template. So we do lithography, deposition, and also resist removal. Then finally we got the square shape YOLO structure. So this is basically on top chromium gold. Then there will be L2O3, and that is insulator, and then there is silicon substrate from the bottom. And this MO is like a structure. So these CV characteristics without any hysteresis. So that tells that, okay, there are less fixed oxide charge in the insulating layer and also negligible leakage current. So that means we can use this as a initial template and we can deposit semiconducting layer on top. So this technique actually describe how we fabricate large scale RES2. So we basically use gold mediated exfoliation technique, and which is described in this reference. And we can even get more than 100 micron by 100 micron large area of RES2, and we can have a device fabrication and finally chip integration for real application. So once we deposit on silicon substrate rhenium disulfide, so you can see it is almost, you cannot, it is almost, there is no optical contrast, so you cannot see even. But if we use this template, initial template, then we can have a chance to, deposit in a particular area. And the initial characterization, Raman, is so the out of plane mode and in plane mode of vibration, and further confirm the high chemical purity of this material, and it confirms the RES2. And so the typical characteristics, which first we do this IV characteristics across this diode, and it's so highly rectifying feature, which you see here. And we again can divide this into various domain, like forward bias and small reverse bias and reverse bias. So in the reverse bias configuration, the minority carriers of these two material are the major, will be the dominated for this electrical conduction, and the minority carrier need to tunnel through this this depletion region at the interface, and to contribute to the current, and that depletion region is the interest for us to show the optical sensitivity. So here what we observe that if we use this rhenium disulfide with different thickness and we make this type of photodiode, then under light illumination with different wavelength, we can see the manifold increment in the dark current. And this current with time, this shows that under successive on-off of this incident light, the current, it also follow the incident light illumination pulse. So it is strongly reproduced, and it is quite fast, and it follow the power law. So basically, if we increase the intensity, the current also get increased. And from there, we extract the parameters like responsivity and external quantum efficiency, which shows that the mixed thickness RES2 based device shows a high external quantum efficiency with fast response of around 10 milliseconds. And that we explain from this band diagram as shown here. So this type of device not only has this depletion region across silicon interface, but also it has those edge state at the interface between thin and thick. So those edge state also play major role in this device response, because they also actually trap carrier so that it increase the carrier lifetime for holes, and that circulate in the external circuit to increase the responsivity value of the device. So next I will talk very briefly about phototransistor, which also we are working on. So it is rhenium disulfide interface with silicon dioxide, and also rhenium disulfide with HBN interface. So we was working on this type of transistor. So we just fabricate on top of silicon dioxide, and we see good gate tunability in the drain current. And under light, we also observe that there is a carrier trapping at the interface between rhenium disulfide and silicon dioxide. So due to the carrier trap at the interface, the threshold voltage actually gets shipped. And that was verified using this type of transistor, where the channel material was lifted up, and there is a air gap between rhenium disulfide and silicon dioxide. So basically, we can neglect the interface trap state. But there is another problem, that we do not have much gate control on the drain current. Of course, there is a good photoconduction over photo gating effect, but we have less tunability. So that we can easily solve by using this type of device, where we use a hexagonal boron nitride as an interfacial layer between rhenium disulfide and silicon dioxide. So that actually suppresses the interface trap state of SiO2. And also it is a quite good dielectric material. So, it will increase the gate control over this drain current. And then we see quite a large enhancement in the current, and threshold voltage also shift at the left, because it is a n-type conductor, and there is a photogenerated holes which actually get accumulated. So there will be a threshold voltage shift. And the photosensitivity value which we see, it is quite huge in this threshold voltage region, with good photocurrent at 532 laser illumination. So basically this will be good candidate for phototransistor application. So next I will talk another interesting project, which is laser assisted multi-level memory. And there we use this combination of rhenium disulfide with hexagonal boron nitride and graphene. So it is a very interesting, because it can store the laser information, input laser information, and it can give the electronic output and it's a dual functionality. So to start with, we again use a dry transfer technique. It is very standard method, and we use a tip which consists of gel packed PDMS and coated with PPC. And then we pick HBN at particular temperature, 40 degrees centigrade, and we deposit on graphene coated substrate at 110 degree. So we start with this graphene, which on the silicon dioxide and silicon, and then we deposit HBN. So we have HBN graphene heterostructure. And then on top, similarly, we can deposit RES2. So basically now we have this type of device, which is shown in the schematic diagram. And if you see this graphene, it is a floating gate, and there is no electrical contact. Basically, it is isolated from this RES2 channel with thin layer of hexagonal boron nitride. And that leads actually various advantages, because it is a 2D surface material, and heterostructure form in a 2D surface. So it has a very large tunnel area, and it can show high switching ratio and also large memory window. As it is a vertical stack, so there is a possibility to increase the integration density of cell. And of course, the electrostatic coupling can be enhanced hugely due to 2D large area. And what initially we observed, that if we actually sweep the gate bias, then we see huge hysteresis in the drain current, as shown here. And if we change the gate field strength, then we actually can reduce the hysteresis, and we can actually decrease the memory window. And we can again do multiple pulses, and we can do the erase and programming process multiple times. So that also give the reproducibility of program and erase step. And various parameters I mentioned here. So we have on-off current ratio can be high, like 10:4, with large memory window, and also low operating bias, like 50 millivolt with pulse of plus minus 10 volt. So the basic operation I have shown here. So to program the device, we need to have a plus 10 volt gate bias. So that actually deform the band alignment across vertical direction, and the conduction electron from this rhenium disulfide can tunnel through HBN, and it can store in the graphene. To read this information, we need to release the gate bias, and we need to apply small drain bias, so that we can read the charge stored information. And to erase that, we again need to apply negative gate voltage, and then again the band deformation will take place in opposite way, so that the stored charge carrier again can tunnel back to the RES2 channel. So this is the operation technique we use, and the retention and endurance we have studied further. So the retention analysis shows that if we program and erase the state, so we can even wait until 8 years, and we can retain the information almost more than 50%. So it has good retention, and also the endurance we have studied until 10⁴ cycles, and it's so very good reproducibility and of this state, erase and program state. Of course, there is a emission and capture process going on in this, so that we get a slow decrement and increase in both. So that cannot be neglected as well. So we are interested with laser assist multi-level operation. So later on, we analyze with this device with light assist, because this rhenium disulfide is a very strong material for optoelectronics. So here we use both as a gate pulse and also laser pulse, and we synchronize them, and we do such that the drain current will follow these two condition. And finally, we can have the erase state, 4 different erase state, depending on the laser intensity we use. So we can have here L1 to L4, as I shown, 4 different state. And here from this figure, we can clearly distinguish 3 different erase state. So first one is without light. So we have only 1 and 0 state. But later on, once we use the laser pulse, then we can have different erase states. So basically 1, 1 and 1, 1 prime. And so from here, you can clearly visualize that it can be used for multi-level. Next, I will talk very brief about this tunnel diode and their logic operation. So basically, we use same structure, but here instead of floating gate, we use this as a drain terminal, and top is the source. And this will give metal, insulator, and semiconductor MIS diode, and that MIS diode has many positive advantage, because it has a rectifying behavior very high with low ideality factor, and this is quantum tunneling diode, so it is less temperature dependent. So the schematic diagram you see here, we can actually fabricate in parallel many MIS diode, and this is AND logic gate operation of this device with truth table. And again, we can use light illumination to have a multi-value logic circuit as well. And the optical image is shown here of this type of device, where we use the thickness of HBN around 10 nanometers. And this is quite good as well for both electron and hole tunneling layer as under sufficient electric field. So initial characterization shows that each one of these parallel diode can have highly rectifying characteristics, as shown from this IV diagram. And if we do analysis for diode, and if we plot them and extract the ideality factor, then we get quite low value like 1.6. And for high field strength, that means at a low bias, if we plot this function, and then the fitting with Fowler-Northam tunneling equation, we can actually see it well fitted. So basically, this FNT tunneling take place for high field strength. So that again confirm that this is a quantum tunneling diode, and this all process can be temperature independent. Further, we can actually use the gate bias, so it can have tunability even under gate. So gate tunable rectifying diode, we can say. And here we saw that the logic gate operation. So basically here it is a very simple operation. We just take two diode and we connect the common graphene as a drain, and we get output voltage. So if the V1 and V2 input bias they are opposite, either 0 or 1, then we actually get always 1, because it is a AND logic gate operation. And similarly, if the level of this input V1 and V2 are exactly same, then the output will output follow the same input as shown here. So it is exactly the replicate of the truth table which we see for AND logic gate. So that means we can use that as a logic and functionality. And again, we can use for even other logic gate like OR gate or other. We just need to connect in different configuration. And lastly, I will talk about another interesting topic which we are interested. It is light emission and its modulation. So here we use monolayer MOS2 because it is a direct bandgap material and it gives luminescence at 680. And we see that these luminescence we can tune further if we couple with plasmonic array, and we can enhance 3-fold to quench 4-volt, so we can have a tunability. So we start with monolayer MOS2 on silicon dioxide silicon substrate, and then we fabricate gold nanocone array on top. So there we select two different type of array. One is double spacing and one is equal spacing. And what we observe under 532 nanometer excitation, that the photoluminescence at 680 nanometer actually get enhanced for double spacing array, and it get quenched for equal spacing array. So that is really very interesting, and we further characterize using this simulation and theoretical approach. So we do the FDDT numerical simulation at the interface between this gold nanocone and MOS2 surface. So at the interface, it shows that the induced electric field, as shown here, so that actually get enhanced. So the line profile of induced electric field intensity is shown here, which shows that the electric field intensity actually get enhanced in both in excitation wavelength and also emission wavelength for double spacing array as compared to equal spacing. And this field enhancement factor has direct link with this PL enhancement factor, because this exciton rate is depend on that field enhancement factor, and that actually can have direct link with emission rate. And this plasmonic array, which actually provide this local density of state to get populate in the A excitons, so that their recombination will give higher luminescence. So that coupling is very strong, and we can further use that for modulating this luminescence. So that's all here. I will conclude that we use various 2D material and their heterostructure to make various optoelectronic device like diode, transistor, and memory device. And these are quite interesting in the field of ultra-thin nanoelectronics and optoelectronics field. So here I have a small announcement. So I am serving as a guest editor for this journal, and we have a special issue on this 2D material based plasmonic nanostructure. So the scopes are mentioned in this link. So if you are interested, you can see, and we are welcome for this paper submission. Thank you very much.
Yeah. So thank you very much, Dr. Bablu, for your interesting talk. So there are a couple of questions from the
Yes.
audience. So I will take the questions. So, but one question is by Professor Tamankar about your trilateral structure transistor devices. So he asked if, as the devices are made in ambient conditions, do you think that there will be water molecules at the interface?
Yes, of course. So when we do fabrication process, the SiO2 surface and also at the interface, we might get also these water molecules. Not only that, even some chemical residue also can stay. So that's what there are those possibilities. So what we do when we do measurement, we do under inert atmosphere and also under sometime a very high vacuum condition. So basically, there will be less effect during the measurement. Yes.
Okay. Another question is about the thickness in your devices, this photodiode devices, rhenium disulfide. How much is the thickness in your devices?
Okay. So actually, in our paper, we have discussed various different thickness. So we start with very thin of 2 to 3 nanometer, of RES2, and we also go very thick. And for mixed thickness, we do intermediate range. So we have a very specific thickness dependent study on this photodiode of RES2 and silicon. And for this mixed thickness, we use 4 to 8 nanometer thick of RES2.
Okay. Okay, thank you for that. One more question is there. This is about your this memory devices using this 2D materials. So
Yes.
the question is about the retention characteristics. Maybe you can show the slides. This retention you reported as around 10 power 4 seconds.
Yes.
But for typical commercial applications, the
Yes.
retention required is around beyond 10 years. So that is
Yes.
around 10 power 8 to 10, about 10 power 8 seconds. So then what you suggest to, I mean, in your devices to improve on the retention?
Yes, actually, we have also, the instrument capability. So we can actually do the highest like 10 is to 4. Maybe we can go until 10 is to 5, but we can always extrapolate in that thing, and we can have a view that how it will perform. So so the so this the endurance, we believe that it can sustain even higher cycles.
I
So
see.
but we do not have such experimental data. So we claim until 10 is to 4, which we have.
Okay. Another question is from Deepak Kumar Panda. He's asking, what is the lattice mismatch between heterostructures? Is there
Lattice
any
means uh,
mismatch between the heterostructure? Is there any lattice mismatch?
yes, actually, these these we these are the 2D material, and we have van der Waals interaction. So we no need to worry much on this lattice mismatch. So we can actually just take one material on top of other, and we can have interface. Of course, we need to sometime do angular, when we deposit, we need to maintain some angle sometime to have higher device performance.
I see.
But is yes.
One question is from another question from Sinu Matthew about for MOS2 plasmon
Yes.
double spacing enhanced PL. The
Yes.
line shape of the main peak seems to have many components. So how about the trion plasmon interaction? So any idea on this?
Yes. Of course, there can have trion formation also, depending on the laser power we use, and also sometimes we use bias to make a charge, and that also give rise trions. But in our study, we here, if you see the photoluminescence spectra, so we do not have such information. So for trion, the full width have maxima of this spectra will be much bigger, and there will be at least small solder. So here also not that much we see, but but we do not have a direct study on that transformation, how much, maybe some percentage we can also extract.
Okay. So since we have a couple of minutes more, so I have one more question from Harsh Chaliawla. So he's asking, what is the effect of number of layers on the photo response and the change in the Fermi level position? On the photo response, how would the number of layers have an effect? I mean, is it good, bad? How will it be?
Yes, that also we are currently another project is going on. So there what we study that for RES2, it gives very good light sensitivity, and also for gas sensing application, even for 6 to 8 nanometer thickness, RES2 will be much better. Because maybe there are some reason that it will have good optical absorption, as well as we need to think about how the carriers actually get collect in the electrodes in the device structure. So we basically give electrical contacts on top of this flake. So not only absorption, we need to see that how photogenerated carriers are getting collected to the top electrodes. So if there is a distribution of photogenerated carriers across the thickness, and that sometimes gives inhomogeneity, or sometimes get lost, and they cannot able to contribute to the device performance. So yes, there need to be further study in details how this thickness can actually affect this optoelectronic device performance.
Okay. So thank you very much, Dr. Bablu Mukherjee, for giving an interesting talk and very informative talk. So thank you very much.
Thank you, Ashutosh.
So yeah, so we are closing this presentation.
Thanks.
Thank you.
Thank you, Doctor.